The initial premise of this project was to devise a lifting apparatus that utilizes a DC motor and an Arduino microcontroller kit to provide further constraints for the project so that the scope of the assignment was narrow enough for the construction and testing of an appropriate math model given a 3-week time frame. We chose to scale down a personal bicycle lift. Our intentions were to develop the first iteration of a logical progression of prototypes to form a fully functional bicycle lift.
For the experimental section, we started by determining the speed of the motor without any gear train reduction first. To do this, we press-fitted one of the shafts of the gear train to the motor shaft. A string attached to the shaft at one end and a mask hanging at the other end. We allowed the motor to run to see how long it would take for the gear train shaft to wind up a specified length of string. This was done for several different masses. To be able to lift more weight, we connected the motor along with the gear train shaft to the actual gear train, and basically did the same procedure as before, with the only difference that the gear train reduction was connected to the motor to reduce the torque on the motor shaft.
The source text used for this project was Hibbler's 11th edition dynamics textbook, from which we pulled rotational motion equations as well as rotational power equations. In the making of our math model, we determined that online specs for our specific motor had insufficient data for our 9-volt experimentation. So, we measured our own torque versus angular speed DC motor curve and idealized it as a way to calculate the input power to the rotating shaft. To calculate output power of the gear train, the concept of work was applied. In order to lift an object, one must do work against gravity. Measuring a differential height over a certain time interval gives one work over time, or power. This power is the actual lifting power that the bicycle would see in a final design. The data from these output power values were then compared to our idealized math model to find results.
One lesson that we learned throughout our experimentation is the use of constant voltage source to ensure consistent results with electrical components. While ideal batteries do provide constant voltage, they are not ideal in real applications. Throughout the span of a project, parts and other variables may be delayed. However, this should not halt or delay overall progress. There are always opportunities to further and bolster other aspects of the project in the meantime. On the Arduino side of things, there are a few things to note. First, push buttons require constant activation to change their variable state, unlike a toggle switch. However, this can be worked around through the use of if statements, in combination with a debounce function, a tool that can be used to ignore signal noise for a specified time frame.